So I'm going to talk a little bit about population synthesis, actually. And let me begin with white dwarfs. So there's many ways that you can create a system where you have a white dwarf and a main sequence companion, which are the things that we're focusing on here on this talk. So you can basically do three different things. You can just not do anything, and you might end up with a main sequence and a white dwarf because it just evolves separately. You might interact through stable mass transfer, or you might interact through unstable mass transfer. And what we wanted to do was to compare this very, very nice data set that we got from Apogee, Gaia, and Galax data for white dwarf main sequence binaries with population synthesis with Katie's code Cosmic. And then with comparing these things, we want to constrain the parameters that we're using for mass transfer inside of Cosmic, and see if we can reproduce this population or not, which is nice. But how we're going to do that? So let me first introduce our data. So we're using this catalog that's combining Apogee, Galax, and Gaia. We're calling it AGGC. So we have a bunch of different white dwarf with a bunch of different types of companions, but we are focusing on the main sequence companions though. And then we can look at, of course, a lot of data that we have from this, but we're focusing also on the radial velocity shifts that we have from this population. And this is just an overview of the population, and I want to particularly call your attention to the delta RP max distribution that we have up there. So let me also explain what I'm talking about when I'm saying delta RP max. So it's a very, very neat thing, because when we observe the systems, a lot of times we don't really have the periods. We know they're in binaries because they have radial velocity shifts, but we don't really have the constraints on the orbital periods of the system, like what it actually looks like. But with delta RV max, we actually have a proxy for the period, because if you have a very large delta RV max, it means that your system is actually very close, because it means that it's going like this, basically, very close. The two stars like interacting a lot. And if your system is further apart, then your maximum shift in the rate of velocity is going to be smaller. So if you have a high delta RV max, that means that you have shorter periods. And if you have a small delta RV max, you have longer periods. Just remember to shift those two. Right. So now I'm going to talk about a little bit about our models. We are changing basically three parameters when we're talking about the mass accretion. We are changing what alpha is. I don't think I have to explain the common envelope alpha here for this audience in particular, which is great. We're also changing the accretion limit, so if the system is conservative or non-conservative mass transferring. And we're also changing the critical mass ratios for the onset of instability using these prescriptions here. So introducing the grid of models that we ran for a bunch of different alphas from 0.25 to the very, from what I understand, very impressive value of 7. We also changed the accretion limit from non-conservative, half conservative, and fully conservative. And we're also exploring a little bit the critical mass ratios. I don't have much time to go into detail about each of these parameters, so I'm going to focus more on the alpha and the accretion limit. Okay, and we're also making sure to make UV cuts in magnitude because we really want to see in our simulations what we would actually observe with Galax and with Gaia and with Apogee. So we're not like looking at systems that are not going to be in the data anyways. And we're also doing a selection cut that we actually only realized yesterday. So these results are very new. That in our simulations, we were actually looking at systems that were still interacting. So we are now cutting those. So we are exclusively looking at systems that went through mass transfer and are currently not doing mass transfer anymore. And just to show you a little bit of our models. So up there we have one model, so alpha equals 7 and accretion limit of 1. And this other one is alpha 25 and accretion limit of 0. Just so you see like what's the different types of interactions that this system goes through, how this changes the period distribution. So the main trend that we see is that if you go through common envelope phase, you end up with shorter periods, which is going to be high delta Argmax. And if you go through basically no mass transfer, then you're just going to have like very long periods because you didn't interact after all. And then if we exclude the systems that didn't go through mass transfer because we don't care about them right now, we can see that most of our population of white dwarf main sequence binaries actually went through common envelope for every single one of our models. And that leads them to have shorter periods, but we also have some population that went only through stable mass transfer, and they tend to have larger periods in general. Okay, so now we want to compare delta Argmax with delta Argmax. So from our models, we have the period, so we have to transform our period into estimates of delta Argmax. So pretending these models are real and that these are real stars in the sky, what we would observe from their delta Argmax. So this I'm basically showing like if we separate the population of white dwarf main sequence binaries that we're looking at, depending on which type of mass transfer they went through, we would see very clear shifts in the delta Argmax distribution of the systems. So what we want to do is compare the models with the data now. Okay. So let's, for instance, take one of my models that has alpha of 0.75 and accretion limits of 0.5 and 1. So I'm going to show like a little suite of models. So in the hashed thing is the data, and each of these guys is one of the models. So D0 is the one with accretion limit 0, 0.5, and then 1. And this is the delta Argmax distribution, and this is the cumulative fraction. So as you may notice, I have a bunch of models. So I have in total 27 models. I'm not going to go into details about every single one of them, but this is the general trend that we're looking at. And then for the models with alpha of 0.25, we also looked at the critical mass ratio. So these are so for this, in this case, the different colors indicate different different critical mass ratios for each of these models. And just going back, in models that look like this, each of the colors indicate actually different mass accretion limits. It's a bit different, but sorry, there was no better way of showing this. And then the point that I want to make is, so if we look at very low alpha with these models have, each of the plots have the same accretion limit, but I'm changing the color means I'm changing the critical mass ratio. And we can see we can change the critical mass ratios, and it only really matters if we choose like this last prescription, which is this pink prescription. And if we also compare like each of the plots, like the general trend of them, we see that they don't change much, which means that changing the accretion limit is also not having that big of an impact on these models. And then if we go for this other suite of models, these ones all have high alphas. And then we can see that high alpha has a very difficult time to explain this tail here of the short delta Argmax, which means the long periods. So it's overestimating the amount of stars that we get with longer periods. Although it is doing more or less decent job of getting the tail of the distribution in the high delta Argmax. And if I just go here, so these are all of my models. Don't think too hard about them. Mostly the thing that I wanted to show is if you look at the models with lower alpha, which are the guys here. So this is alpha of 0.25 and 0.75. They seem to be doing a better job in general of explaining our population. So this is very nice because this was part of my Kavli summer school project, and the result that we had then was that high alpha was favored, but since we did all the correct cuts in the data and in the models, now we have something that makes more sense, because we had alpha equal 9 at some point as the best model, which was a bit insane. But yeah, I think I can just go to the conclusions because I don't have much time. Okay. Right. So basically what we found is that lower alpha is favored, and the effect of the accretion limit is smaller than the effect that we have from changing alpha and from changing critical mass ratios, which basically means this makes sense because most of our white dwarf main sequence population ends up being formed through a common envelope rather than mass transfer. So if we change the parameters that are more connected with common envelope, such as when these things become unstable and the alpha vector, then of course you're going to have a bigger effect overall in the population. And we also have some questions because this is an ongoing project. So maybe some of you have an idea of what would be the best way to really compare the observations and data in terms of statistics, and if delta RV max is really the best parameter that we could be looking at when we're talking about these things. And thank you very much.
Julie has a question online. She was first, and then I'll bring it over here.
Really great project. Really like it. I have a question because we know a little bit about the formation of white dwarf main sequence binaries, where the main sequence star is very low mass, so less than 0.5, like M dwarfs. And there indeed, like low alpha is clearly favored. There's multiple papers on that. But what the observations show is a gap. So we're finding observationally systems with periods up to several days, like 5, 6, 7, and then there is a gap. And then the question is, when does it start again? But if I look at this RV max distribution, it seems pretty continuous. So is that really true here? And at the same time, how different is this population? So what type of main sequence stars are in this data set?
Right. So I'm not doing really a cut on what type of main sequence star we're looking at. We're just looking at all the main sequence stars. But about the period gap, we do find an interesting period gap. I didn't go into detail because I really didn't have time. But in the models, we do find, depending on the model you're looking at, you find a period gap that shifts a little bit depending on what your common envelope parameters are. But yeah, we found a gap at about 200 days, if I'm not mistaken. So around that region, we pretty much find no systems at all. Maybe Katie wants to say something.
Can I talk on the mic? Thanks.
The observation is pretty continuous, or
they are in delta RV max, but I think the gap gets a little bit washed out because it's below delta RV max. And so you're much less sensitive when you're using delta RV max to those longer periods. The gap does appear to persist in this data set with Gaia astrometry. We've been talking with Karim about this. He's been doing cross matches. It doesn't persist in the SDS in a different sample. So everyone's very confused about the gap. But I think you're right that looking at the mass constraints is a really good idea. So the apogee, this AGGC is from apogee, and apogee has a really narrow temperature range. So we're pretty much sensitive to like one solar mass stars plus or minus a couple, like 0.2 or so. So it's really close to one-ish solar mass.
So these systems are found because you see a main sequence star moving, but you don't see a complex. It wants to be a white dwarf.
Yeah, exactly. So we select first on them having radial velocity variations in apogee, and then do the UV selection. So we're very much biased to the apogee temperature selection.
Cool. Thank you.
There's a question here, Kyle.
Oh yeah, thank you for the talk. I had a question about the data, the CDF. I would imagine that the low RV maxes, you have a lot more samples versus like the very high end.
Yeah.
And so there's like a variable variance across your observational CDF. So I was wondering, like, when I was looking at the comparison between like the models and the data, should I look at a discrepancy, like on the far left of these CDFs, and be
Yeah, the
like-
normalization, right?
Yeah, yeah.
Yeah, we're really trying to figure out what is, that's why I asked actually at the end, like, is this the best thing statistically that we should be looking at? Are we supposed to be looking at cumulative fractions, or is there a better way of looking at these things? Because, yeah, as you said, there's a lot more systems here at low delta RV max than we have here at high delta RV max, and even in the data, like, maybe you can see here like that the data just has this step thing. So this is like 2 systems or something, 1 system. So we're pretty limited in that sense.
So one thing to state, sorry, thanks. The width of so what Amanda has done is sample hundreds of populations to look at the variance in the delta RV max measurements. So the width of the spread here, I think, is a good indicator of how uncertain the delta RV max observed delta RV max distribution is. If we had perfect fits to everything, then it would be the width of the line, right? But we don't. So
Yeah.
So yeah, you were asking there are additional information in your data set that you're not using. One of them is the time difference or the time base at which those large or small rate of velocity variation is occurring. And you can also look at correlation between time and velocities. We try to do something similar for a completely different project, but we're looking for binaries, and we only had a few epochs.
Right.
We model the period distribution and mass ratio distribution, simply modeling different quantities from the rate of velocity measurements. So you can have a look at that. Maybe you'll find inspiration.
That's great. Thank you.
I have a question myself as well, and then people should raise their hand if they have a quick question. But I was very curious to the purely stable mass transfer systems that you found. And specifically, I think if you split out your cumulative distribution functions between the common envelope channel and things that do go through common envelope and things that don't go to common envelope, I think you will see all the effect. And this is also what you hinted towards. But specifically, I'm surprised that you still get systems that manage to stable mass transfer, and then on the way back are not such extreme mass ratios that they go common envelope. And yeah, I would be really interested in seeing what that population does if you change the mass ratio of stability and the accretion fraction that you both varied, because they should die. And if they don't, I'm a little worried.
Right. Yeah, we did. I can show more plots. Plots that I think show what you want to see more clearly than this. So
they do die. Okay.
Yeah, they merge. There's a lot more
in
merge.
the first place. So a little bit that you have basically zero accretion efficiency, or what is it?
Yeah, I think in most of the cases where we keep them, they have zero accretion efficiency.
Okay, so that might also have other observables then of them like never being spun up. Okay, we should.